There are many beautiful examples of how MJOs and oceans interact at lower frequencies, in the sense that MJO is an intra-seasonal timescale process, but in a year, in a season, let's say you have multiple MJOs, they actually produce a low frequency rectification in the ocean in terms of mixed layer depth, stomach line depth, nutrient entrainment, chlorophyll, and so on. So the seasonal amount of chlorophyll, for example, and nutrient consumption is different in a year with more MJOs than in a year with fewer MJOs because of this low frequency rectification. And the other question is, how does the low frequency rectification feed back to the MJOs? Is there a potential for such a feedback? And these are few papers by Zhao Lei which looked at the feedbacks, and he focused on a specific thing. He started by, I hope this is by looking at the measure of barotropic instability, which is the gradient of planetary vorticity versus relative vorticity, so beta minus uyy. And when you look at the this quantity here, if the planetary vorticity and relative vorticity produce these positives and negatives, then it indicates instability that then can be triggered into eddy kinetic energy. So there is a vertical shear, typically as a baroclinic instability, which creates which creates eddy kinetic energy, or it projects onto waves, and then you have to see where the waves go and what they do and at what time scales they do what they do. Okay, so if you look at the barotropic energy conversion versus baroclinic energy conversion, I won't go into the details of the formula for so here is barotropic, and it's generally negligible, whereas when you look at baroclinic instability, it is fairly strong. dq dy equals beta minus d squared u dy squared, so that's uyy, and here dq dy equals beta minus d squared u dy squared. So this is okay, barotropic and baroclinic instabilities. Basically, you can read Zhao Lei's paper to make sure I didn't screw that up. But essentially, the main point is that the during the MJO period, fall and winter months of the boreal seasons, so northern hemisphere fall and winter, the barotropic energy conversion is minimal in the southern Indian Ocean, so you're going from 5 south to about 25 south here. The baroclinic energy conversion, you can see this is 10 to the minus 5 watts per meter cube. Shouldn't be over meter minus 3, but anyway, this is order 10 to the minus 3. So much more baroclinic energy conversion is happening. And the main idea, you can look here at the baroclinic energy conversion in January, April, July, and October. So typically the October, April is the MJO season. And the idea is that MJOs, which are propagating eastward and kicking off these Kelvin waves that we talked about, are producing equatorial Kelvin waves, are converting into coastal Kelvin waves, and the ones that go south are interacting with the Indonesian through flow and creating baroclinic instability in the MJO season, and that instability is being released into Rossby waves, which propagate westward, and since they are at a latitude of about 10 to 15 south, they are going to disperse equatorward because their phase speed is dependent on latitude. You can read up about the basics of Rossby waves, or you can look at my podcasts in Tropical Dynamics course, for example. And the Indonesian through flow is centered on the thermocline. It's not surface intensified, but it is thermocline intensified. And the downwelling Kelvin wave is also pushing the thermocline down. So the energy conversion is centered on the thermocline. So you can see here in January, in April there is some, in July there is not much because that's the meso season, whereas in December you get again thermocline intensified baroclinic energy conversion. The same story here, even though you do some signature, the maxima are here in these months. Okay, you can use something called the ED model. There is a current coming out of here. It's called the I hope it's the South Equatorial Current, which is like a jet which carries the Indonesian through flow waters eastward, westward, which then goes south into the Mozambique Channel, and then does interactions with the Agulhas retroflexion and Agulhas outflow and so on. The ED model, basically there are some assumptions involved, but it's an instability model for the zonal jets, like the jet stream, for example, and you can see what the growth rates of the instability being released into the waves are, and what the time scales of those waves are. So here it's looking at scale of maximum instability in December. So that's of this order here, orders 500 to 700 kilometers, which is typical of a Rossby wave scale in the ocean at these latitudes. The latitude dependence is very important, and it's picking inverse of the growth rate. I'm not going into the details of the ED model because it's mathematical, it's a bit complicated, but the main point I would want you to leave with is that the instability that is created here by the eastward downwelling Kelvin waves created by MJOs propagating down, as downwelling coastal Kelvin waves are interacting with the through flow that's coming through here, creating baroclinic instability here, which gets triggered into waves. Then you have to figure out the scale of those waves and the time scales of those waves. So you can see that this is basically in the 20 to 100 days, which is the intra-seasonal time scale. Okay, so the MJOs themselves are creating an instability, and they are sending the instability is sending Rossby waves back to this region because the Rossby waves which propagate westward are dispersing equatorward along the way because of the latitudinal dependence of the phase speed of Rossby waves, which means they end up returning to the region which is very typical of MJO genesis, right? Western Indian Ocean. So the question is, can the MJOs feed back to themselves through this process of ocean instability and returning Rossby waves? It turns out that they can, because this paper of Zaule does heat budget analysis and shows that the instability and the waves that are created here are actually altering the heat budget of the mixed layer in this region, which is the MJO genesis region, and there are details that it actually has a warming during an entrainment because it creates a inversion in temperature, which means the surface temperatures are colder than the subsurface temperatures. So when entrainment happens during the fall winter months, warmer waters are being entrained into the mixed layer and affecting SSTs, and potentially are able to affect the MJO genesis. The question, of course, is if such a loop exists, and knowing that the MJOs, the Rossby waves will take 12 to 24 months to go from this region here in the Southeast Indian Ocean back to this region in the Southern Tropical Indian Ocean. What are the potential feedbacks? If it is a positive feedback from MJOs to MJOs, then obviously you need a break and the negative feedback somewhere to cut off the growing modes. If it's a negative feedback, then you have to understand how MJO variability on different years, or interannual variability of the MJOs in terms of the number of MJOs or their amplitudes and frequencies and so on. How are they affected by the negative feedback? So this just indicates again that oceanic intraseasonal variabilities are naturally generated because the barocclitic instability is projecting onto the intraseasonal time scale as well, and those Rossby waves are propagating back towards the southwestern Indian Ocean into the MJO genesis region and affecting the heat budget. So this is just a diagnostic which shows that such a loop exists and that this could potentially have an influence because it affects the heat budget in the critical MJO genesis region. But you will need serious coupled model experiments to understand how this feedback is actually working, whether it's positive feedback, whether it's a negative feedback, and what it means in terms of MJO variability itself, or what it means in terms of how MJO is able to feed back to its own genesis through this oceanic pathways. So another good example of ocean's role in the MJO dynamics. Okay, so that's ocean intraseasonal variability, but also responding to MJOs and feeding back to the MJOs. That's the goal of this section on ocean intraseasonal variabilities. Okay, we will leave it here.